Good morning dear students, and today I came here with one more new topic, that is packing of constituents in the crystals, or also called as what packing of solids. And it is somewhat interesting topic and somewhat confusing also, but once you go through this topic clearly and you may not get any confusion. And here it is one of the important topic also for the competitive examination. Let us see. Here you know that, so before going to start this topic, so in the solids, at the that is introduction of this chapter, I told you that in case of solids, atoms are very close to each other, means they are very close to each other. The intermolecular distance between the atoms is very low, means they are very close packed to each other. So due to this close packing only, the solids are having a definite shape and they occupies definite value. And here how the solids can be packed, means how the atoms, means here constituents are nothing but atoms which are present in the solid. How these atoms or the constituents can be packed in the solid. To understand this concept, we must know about three types of the packing here. The first one is close packing in the one dimension. Second one, close packing in the two dimension. Next one, we have close packing in the three dimension. See, the 2D dimension can be understood clearly, so on the board, but the 3D dimension is somewhat difficult. So to understand this concept on the board, because it is we actually require the 3D pictures here, so it is impossible to show on the board, but I will try my level best to understand this concept. So listen now. See, first we are discussing about the close packing in the one dimension. So see that in case of close packing in the one dimension, for example, here the atoms can be marked as AB, 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 like AB atoms. Atoms are arranged like this. So here they are arranged in only one row, not in a two dimension, only one dimension. They are arranged here in a row. You see that, for example, any atom you take, not only B. See, this B is surrounded with how many atoms? Two other atoms. So neighboring, it is surrounding with the two atoms. Therefore, so here the number of the atoms surrounded by, or number of the neighboring atoms surrounded by any atom is called as coordination number. Once again I repeat the definition of coordination number. Number of the atoms surrounded, number of the neighborhood atoms surrounded by any atom is called as what? Coordination number. Here the B is surrounded with how many number of the atoms? Two atoms. These two A atoms are surrounding with the B. Therefore, the coordination number of the B is how much? 2 here. Therefore, we are writing in case of one dimension, what is the coordination number? 2. Because each atom is surrounding with how many atoms? 2 atoms. Next one, second type of the packing here, close packing in two dimension. Let us see this close packing in the two dimension. See, this kind of the close packing in the two dimension can be done in two ways. The first one is square close packing. So what is this square close packing? And next one is what? Hexagonal close packing. See the difference between these two. To understand this clearly, here we have two types of the diagram. You see that this is the first row of the atoms in a solid, second row and third row, and you can arrange fourth row also. Once you observe this clearly, the second row atoms, this is the first row and it is the second row. The second row atoms are exactly. Otherwise, you see that the first row atom. Just take the first row atom. First row atoms are exactly on the surface of second row atoms. You see that this one is an exact of this one, fourth one. So therefore, first row atoms are exactly. That is surface or top of the second row atoms. First row atoms are exactly sitting on the first to second row atoms. See here, you see that, for example, you take here, this is the central atom we have. So this is the central atom. In this, it is surrounded with how many number of the atom? 1, 2, 3, 4. These two atoms are not touching. That's why I am not giving the number. You see that here we have gap here. They are not touching with each other. Only how many atoms are, that is, just imagine like this is an A atom, center one is A. This A atom is touching with how many number atom? 1, 2, 3, 4. Therefore, what is the coordination number in this type of the close packing? 4. In case of square close packing of 2 dimension, what is the coordination number of each atom? 4. Once again I repeat that. See that first row atoms are exactly top of the surface of the second row atom. Each atom is surrounding with how many number of the atoms? 4 neighborhood atoms. Therefore, what is the coordination number? 4. Next one we have hexagonal close pack. Observe this one close packing. Square close packing we are calling because you see that if you connect all the atom, it looks like a square only. Therefore, it is called as what? Square close pack. And hexagonal close packing, you see that. This is the first row, second row, third row, like next fourth row you can take. You see that the second row atoms, observe clearly, these yellow color second row atoms are present in the depressions. Here you see that in between these two. So for example, you take two balls. When you connect two balls, that two balls cannot be connected with 100% efficiency. There is some gap is forming between two balls. So this is a gap which is forming between the two balls in empty space. So in this empty space, the second row atoms are arranging. Means the second row atoms are present at the depressions of the first row. Depressions of the first row. This gap is called as a depression. The gap which is present between the two atoms is called as one depression. This one. In this depression, the atoms are locating. Which atoms are locating? Second row atom. So you see that these two atoms depression here. Therefore, this atom is locating. Now here one atom in between these two depression. In between these two depression, this atom. So therefore, exactly the key point here. The second row atoms are present, are locating at the depressions of what? First row. So that kind of the arrangement is called as what? Hexagonal close packing of 2 dimension. Now in this, you see that here, just imagine like it is also an X atom. This X atom is attached with or surrounded with how many number of atoms? 1, 2, 3, 4, 5, 6. It is touching with all the atoms, 6 atoms. Therefore, what is the coordination number here? 6. So whereas in case of square close packing, one atom is surrounding with 4 atoms, therefore coordination number 4. But here, this X atom is surrounding with how many number of atoms? 6. Then what is the coordination number 6? And here why we are calling hexagonal close packing? Because it just looks like by connecting all the atoms, it looks like a hexagon. Like this. It looks like this. Therefore, it is called as what? Hexagonal close pack. Is it clear? These two. And now we will go for this third one. So, square close packing in 3 dimension. And here, this is very important concept and somewhat difficult also. And 3D diagrams we required actually. Let us see that the first one we have again square close pack. It just look like a 2 dimension only, but in this case the atoms are arranged in the 3 dimension. So is it clear? Here first row atoms are exactly placing on the top of the second row atoms. Like this in case of 2D dimension. Is it clear? Exactly keeping on the surface of the second row atom, but we are placing here it is in a 3 dimension. 3D dimension we are putting the atoms. So in this case also, what is the coordination number? Each atom is connecting with how many number of atoms? 6 atoms. You just see that. So if we take like this, 1, 2, 3, 4, 5, 6, like totally 6 atoms are connecting. Therefore, what is the coordination number? 6. Is it clear? And it is just like a 2-dimensional square close packing, but atoms are arranged in 3D dimension. So that is the difference. And now we have hexagonal close packing. It is very important. In case of hexagonal close packing, you just see that your atoms are again placed in the depressions. Atoms are placed in the again what? Just you see that. These are the second row atoms we have. Just see this. So here, second row atoms. So in this A first row, and here these are second row atom, white color. So this second row, not yellow color, white color this one. second row atoms are placed on the depressions of first row, but here one more atom also we are placing because it is a 3D dimension. And to understand this clearly, I am writing like this. Here you see that I can put the atoms like this. Okay. So this is first row and second row atoms like that. And here I am placing one more atom. Just imagine like this here. So first we are arranging first row these. So these are A first row and next second row. On this I am placing one more atom. Okay. Totally how many atoms are there in this? 4 atoms. Okay. Just imagine you just take 4 balls and attach all the 4 balls like this manner. Means just keep 2 balls here and one more ball below. And top of this one more ball, and you see that from the back side. Have you got my point here? These two are first row, next second row. On this I am connecting one more ball. Then once you see the back side, here some gap we can find here. Is it clear? So these are called as a void. Means atoms are not connecting with 100%. Okay, some gap we can find here. So this is called as what? Void we are calling. So in this kind of arrangement, you see that here the void is forming. So you just go through this. The void can be observed here only. 1, 2, 3, and one more atom I am placing here. This one. 1, 2, 3, and one more we are placing on this. Here you can find the void. So this is the void we are forming. In this void, how many atoms are there? You see that 1, 2, 3, 4. One more we are placing. Therefore, 4 atoms are there. This void is called as a tetrahedral void. Which void we are calling it is tetrahedral void. Is it clear? And one more kind of the void is also forming here. So what is that void? To understand this, so in this diagram you may get confused, but I can explain with you by taking similar diagram like this. So when you arrange like this, here you can form one more kind of the void here. That void can be taken as like this. So I can show you the both type of the voids in case of hexagonal close packing. So that is, this is a void which is forming here. So that first row, second row, and I am placing one more atom on this with yellow color, this one. So this void is called as a tetrahedral void. In some gap you can find between the 4 atoms, therefore it is called as a tetrahedral. And one more type of the void is also forming. Let us see that also. Okay, so first one, first row, second row, and you see that I can arrange atoms like this also. Okay, so here 1, 2, 3. And I am placing another 3 atoms, 1, 2, 3 like this. Okay, just I am showing here 3, 4th one, 5th one, 6th one. 6 atoms are arranged in this void. Here you see that again the gap is forming. Okay, so this gap is called as a octahedral void. Okay, so there are 2 types of the voids are forming in the hexagonal close pack. The void which is forming by surrounding the 4 atoms is called as what? Tetrahedral void. And the void which is forming by the surrounding the 6 atoms is called as what? Octahedral void. And about this tetrahedral void, octahedral void, the next coming class we will discuss clearly. And how the tetrahedral voids, octahedral voids are located in the cubic close packing, and also in the body centered cubic close packing, hexagonal close packing. So that we will discuss in the next coming class in detail. So thank you.